Hello everyone. My name is Mayank Sharma and I'm an applied scientist at Amazon Prime Video International Expansion team. Welcome to the third lecture in the supervised learning module. So today I shall be discussing some of the evaluation metrics and supplementary topics in supervised learning. The order of the presentation will be as follows. We'll discuss some of the evaluation metrics which are typically used for classification and regression tasks. We'll talk about how multi-class classification is performed. We'll talk about some of the classifiers which are typically used, such as naive Bayes classifier, k-nearest neighbor classifier, support vector machine classifier. And then we'll finally talk about how do you perform model selection. So let's begin with evaluation metric. Now, evaluation metrics explain the performance of a model. Evaluating a model is core part of building an effective machine learning model pipeline. What happens is that generally you build a model, you get feedback from the metrics which you compute about the model. You make improvements to the model based on those metrics, and then you continue that process until you achieve a desired level of, let's say, accuracy. Now, the choice of the metric completely depends on the type of model and the problem at hand which you're working on. So we shall cover the following classification and regression metrics as shown on this slide. Now, let's look at a problem of predicting if a customer transaction is fraudulent or not. So on the figure, what you see is the order stream, right? The blue ones or the blue points are the good orders, and the red one are fraudulent orders. Now, what you would do naively, you would manually look at each of these points or each of these orders, assess the attributes or the features of these orders, and decide whether this order is fraudulent or not. However, this is not scalable process, right? With millions of transactions happening, let's say on Amazon, doing it manually is very difficult. So what do? You automate the process by building a machine learning model. What that machine learning model does, it scores these transactions based on some of the features of these transactions. And then it provides a risk score, right? Higher the risk score, the more chances it is for that transaction to be fraudulent. Lower the risk score, lower are the chances for that transaction to be non-fraudulent, or it's a good transaction. So using this machine learning model, you get a good separation of the data. However, please note that the separation can never be perfect, because it might so happen that some of the fraudulent transaction would look like good transaction and vice versa. Okay. Now, as I said, the machine learning model will provide you a risk score. Higher it's bad, lower it's good. Now, typically these scores are probabilistic, as you have already studied in the previous lectures, right? So you get a probability that an order, it's a fraud or it's a good transaction, right? And then you rank them, right, based on the order of the score. So this is the kind of segregation you get. If your model is good, you get a good separation of good and bad score. Otherwise, you don't get a good separation, right? So right now we can say that, hey, our model is pretty decent because the red or the fraudulent are on one side, and blue or non-fraudulent are on the other side. And as I said, the model is never perfect, so there may be some mix and match here and there. Okay. So where would you draw a line, right, which would separate these two classes, right, or these two categories, fraudulent and non-fraudulent? Where would you draw a line, right? I would typically draw somewhere here, right? Okay. So typically what we do in a machine learning model, once you train it, we select some probability threshold. Let's say we select a threshold of 0.5 and say that all the transactions with score greater than 0.5 are fraudulent, and all the transactions with scores or probability less than 0.5 are non-fraudulent. As I said, separation may or may not be perfect. Okay. So what happens is, once you tag something as fraudulent, this goes to humans to verify whether this is actually a fraudulent transaction or not. Okay. While doing so, what might so happen is there might be these non-fraudulent transactions which would also go to human, and then it might take some time for human to verify. You might delay some order, but it's better than uh, allowing these fraudulent transactions to pass by. Okay. Now, what happens if you change the threshold, right? Let's say you change the, initially it was 0.5, now it's, let's say, 0.3, right? So what would happen here in this case is more and more transaction on the right side of this threshold would be marked as fraud, and more of them would go to humans, right? So the effort of humans in checking of these transactions would increase, right? Because more transactions are going to humans now, and will delay the orders. What would happen if you, let's say, select a threshold of 0.8 or zero point 0.9, which is something like this, more towards the right side? What would happen in that case is lesser number of fraudulent transaction would go to humans, and more fraudulent transaction would pass through, right? And this would cause dearly for the company. You don't want that these fraudulent transaction to pass by, right? So it's pretty important to select the right threshold, which actually separates out the data in the best way, right? And how do you select this threshold is based again on the problem at hand and the metrics which you choose for that problem. So we'll now move towards explaining these metrics or these choices of metrics, right? So the first thing we'll talk about is a confusion matrix. A confusion matrix is an n by n matrix where n is the number of classes which are being predicted. Uh, Typically, it's basically a performance measurement for a classification algorithm where, as I said, it can be binary or a multi-class classification. So typically for a binary classification, on the left-hand side, you'll see an example, pictorial example. For, let's say, for each of the sample, you might have a true label, which is either 1 or a 0. So this is the true label. Similarly, based on the thresholding, the model would either predict 1 or a 0 for that given data point, right? So let's take this example. So there can be 4 possible cases, right? When the actual value is 1 and your predicted value is 1, it's known as true positive. So this example specifies this. So let's say a pregnant woman goes to a gynecologist, and gynecologist, after assessing the condition, says that the woman is pregnant. This is a true positive case. Let's talk about true negative case. If a male goes to a gynecologist and then the gynecologist says that you're not pregnant because it's unlikely for a male to get pregnant, and hence this is a true negative, right? Because the actual value is also 0, predicted value is also 0. What happens, let's say a male goes to a gynecologist and he says that, hey, you're pregnant. This is typically not possible, and hence this is false positive, because the model, which is the gynecologist, it's saying the male is pregnant, which is positive case, and it is wrong, and hence it is false positive. Similarly, you have false negative case, right? A woman goes to a gynecologist, she is actually pregnant, the true value is 1, however the gynecologist says you are not pregnant, so this is false negative case, right? On the right hand side, this is a concise representation of the same figure. TP represent true positive, FP represent false positive, FN represent false negative, and TN represent false negatives. Okay, now consider the figure on the right hand side, right? So just consider this square for now, and this center line, right? Uh, Anything to the left of the center line is a positive example. True positive, the actual labels of these are 1. Anything on the right hand side, which is the light gray region, and this pink region, is basically uh, uh, all the examples with true label as 0, right? Let's consider 1 and 0 for now. Now consider a machine learning classification model with some threshold, right? So anything, this is what a machine learning model predicts. Anything inside this circle, the model predicts as 1. It may or may not be right, as you can see from the figure. Anything which is outside this circle, the model predicts as 0, right? Again, the model may or may not be perfectly correct. Okay. Okay, so anything which is inside this green semicircle indicates true positive. That is, the whatever the model has predicted as 1, and they are all the true. The actual label is also 1. The pink classes are the false positive cases. That is, model has predicted them to be 1. However, their actual label is 0, and hence these are false positive. Anything in this region to the left of the semicircle and the dark gray region is false negative because their actual label was 1. However, the model has predicted them to be 0. Anything on the right and outside this peach or the pink color are the true negative because model has predicted them to be negative and their true label was also negative or 0. Okay, so we'll compute the following metrics such as precision, recall, false positive rate, true negative rate, and so on and so forth. So let's talk about what is precision, right? Precision is basically what it says is how correct you are on the ones you have predicted as positive, right? So take this example, pictorially example, this would be really helpful in understanding. So precision is basically this green semicircle to this complete circle, right? Which it says that how many actual positive it predicted to the total positives it predicted, right? So this is precision. Similarly, you can compute the recall. Again, look for this figure for recall here, which says that what fraction of positives did you correctly predict, right? So the model might not predict all the positives, all the actual positive as positive. It might only predict a fraction of them as positive, and that fraction is known as recall. It is also known as sensitivity or true positive rate, right? As the name suggests, true positive rate means the true positives from the model to the total positive, right? And hence the name true positivity rate. Similarly, you can also compute false positivity rate. As the name suggests, what the false positivity rate is the fraction of negative samples which you correctly predicted, which you wrongly predicted, right? Okay, so these are the false positive which the model predicted, right? So this speech segment, and the total negatives were this, right? These were the actual negative. So it's basically the ratio that how many false positive you selected out of the total negative samples. So this is the false positive rate. Similarly, you can also compute true negativity rate. The true negativity rate is basically the fraction of actual negative samples which you correctly predicted, right? So from this figure, this is the sample set which the model said, hey, I am confident that these are negative to the total negative. So this is the true negativity rate, or it is known as specificity. Okay. There are also two different other matrices which you typically compute for a given classification model, right? Let's say your data set is balanced, right, with equal number of samples in each class. So what you do is you also compute the accuracy of the model, right? The accuracy is denoted as the ratio of total correct prediction to the total number of samples, right? So the total correct predictions were this green block and this part of the square where the model has predicted the true negatives. So it's basically the sum of true positive plus true negative divided by the total number of samples, right? However, for imbalanced data set wherein the number of samples of one class is pretty higher than the number of sample of the other class, the accuracy metric is misleading. Now let's take an example. Consider that your data set contains 95 negative samples and 5 positive samples, right? And your model predicts everything else negative, right? So if you compute the accuracy in this case, it would be 95% accuracy or 0.95. I have not multiplied by 100. Okay. You can also multiply it by 100 to get 95% accuracy. So is this the right metric you should look for? No, because you're not taking into account these 5 positive classes or these rare classes, right? And hence the accuracy is not the right metric. So what you do in this case is you compute the balanced accuracy measure. What it does is that it normalizes the true positive and the true negative prediction by the total number of positive and negative samples. So you are taking into account the amount of positive and the negative samples, right? So what you do is you take the true positive samples, you divide it by the total number of positive samples. You take the true negative samples, you divide it by the total number of negative samples, and you take the average of the two, right? So if for the above example of 95 negative and 5 positive values, for the first negative class, you get a balanced you get the true positivity rate of 1. For the other classes, you are not predicting anything, you get a true negativity rate of 0. You take the average and you get a value of 0.5. This is a better measure than accuracy, right? You're saying, hey, my model is 95% accurate, but you're not selecting anything about the other class. However, this takes into account the imbalance, and hence this is a better measure. Okay, now let's take an example to understand more, right? Let the true labels for a given 7 samples with this, right? 0, 1, 0, 1, so on and so forth. You have the predicted scores, which are probabilistic, right? For a given classifier, 0.5, 0.9, 0.7, 0.7, so on and so forth. Then what do you do? As I said, you select a threshold and you say above this threshold, the predicted label is 1. Below this threshold, the predicted label is 0. Let's select the threshold of 0.6. So for this sample, the label predicted label would be 0. For this, the predicted label would be 1, 1, 1, 0, 0, 0. Okay. Now let's compute accuracy, recall, and precision. So let's first compute accuracy, right? Now, what is accuracy? As I said, total number of correct predictions to the total number of samples, right? So in this case, the total number of correct predictions are basically 4, right? So here, 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 and here. The model has predicted 0 and the actual label is 0. Model has predicted 1. This is also 1, and so on and so forth. So the accuracy is 4 divided by total number of samples, which is 4 by 7. Now let's compute recall, right? What does recall say? Recall says that what is it true positive to the total number of positive cases, right? The true positive cases are only these 2, right? And the total positive cases are these 4, right? Total actual positive cases. So the recall would be 2 by 4, which is 1 by 2. Let's compute precision, right? Precision is the ratio of true positive to true positive plus false positive, right? So true positive to the total number of positive which are predicted by the model, not the actual values. So total true positive are 2, and this is 1 false positive, right? Because the model has predicted 1 and the actual number is 0, right? So in this case, the precision would be 2 by 3. These 2 divided by total number of true values which are predicted by the model, true positive plus false positive cases. Okay. Now, when deploying a model in real life, as I said, you have to take into account various metrics, various thresholds, right? So a good practice is to plot a precision recall curve, right? And as I said, how do you decide the threshold? The threshold depends on the problem at hand. So let's take an example. So on the right-hand side, you'll see a precision recall curve. On the y-axis, you have precision. On the x-axis, you have recall. And this plot is basically you select different thresholds, right? And for that threshold, you compute recall. Let's say compute precision and recall for threshold of 0.9, 0.8, 0.7, 0.6, 0.5, 0.4, 0.3, 0.2, 0.1, and 0, right? And you get a curve. So let's take the first example, right? Where let's take an example of movie recommendation in Prime Video, right? Okay. So you open a Prime Video page, you select that, hey, show me a movie based on, let's say, some genre X, right? The genre can be action, comedy, drama, and so on and so forth. Now, if you're, what you would ideally like, right? We would ideally like to recommend the correct genres of movies, right? Even though we may miss out on several movies of that same genre, right? You would want to show that, hey, these are the possible some subset of collection of the movies which belong to the same genre. You may or may not want to show all the movies in that genre to the user, right? So what does this mean is that you want high true positivity rate, right? Which implies you want you don't want to show movies of wrong genre, right? If you have selected comedy, right, you don't want to show an action movie to the user, right? And hence, which implies you need high precision here, right? So you plot the precision recall curve at various threshold, and then you choose you choose a threshold such that the precision is high, but you may be okay with low recall. Okay, so this is the first case. Now, consider a rare event detection case, right? Such as, let's say, a cancer detection or a COVID detection, right? Now, You would ideally want that if a person has a disease, it should be caught during the test, right? You don't want that it should not be caught during the test, and that would have disaster consequences, right? So, which implies you're going with high recall value, right? So, which it says that whenever it exists, you should catch it, right? Which implies high recall, right? We may be okay with lower precision in this case, right? Because you can, if the even if you flag somebody as having cancer, you can go for another round of test, and then it would be um, nullified there, even if the person don't have a cancer. Okay. Now, there's another metric known as receiver operating characteristic curve, or ROC curve, and then I'll also talk about AUC. Now, the ROC curve is a graphical plot, right, as shown here, that illustrates the diagnostic ability of a binary classifier system as you vary the threshold for that system, right? So, how this ROC curve is created? On the x-axis, you have a false positivity rate. On the y-axis, you have the true positivity rate. Okay. And then let's take an example of a model as shown in blue, right? You again, same thing you do in precision recall curve. You select a threshold, you compute precision recall. Here you'll compute true positivity rate and false positivity rate, right? Let's say at a threshold of 0.1, this is the value. At 0.2, this is the value. 0.6, this is the value. 0.7, this is the value. 0.8, this is the value. 0.9, this is the value, and so on and so forth. Right. So as the threshold is varied, you compute true positivity rate and false positivity rate, and you plot it. Right. Now, the best classifier ideally would be you want a zero false positivity rate and a very high true positivity rate. So 0, 1 in this plot would be the perfect classifier. But generally, this does not happen because of the variability in the data itself. Right. The diagonal line divides the plane into two parts, right? This diagonal line is associated with a random classifier. Random means you toss a coin and then randomly provide the output for a given problem, right? So you'll get this line. Okay. Anything which is above this random classifier is good. And let's consider these three models, right? So as I said, going this way is better, going this way is worse, because by going this way, you're going towards the perfect classifier, which has zero false positive rate, that is, does not make mistake and always predict something which is true, right? So you ideally would want to push this way. Now, out of these three, which one would be the best classifier, right? Let's say you have three different type of classifier, and these are the ROC curve for these three classifiers. So which would be the best? The blue one would be the best because it is more closer to the perfect classifier value. A bit of trivia about the name ROC, right? We talk about ROC and all, receiver operating characteristic. What does this name mean? So the ROC curve was first used during the World War II, and it was used for the analysis of radar signal. Now, why it was used? Following the attack on Pearl Harbor in 1941 by Japanese army, the US army wanted to know the prediction, how good the prediction is to detect the Japanese aircraft from their radar signal. And for this purpose, they measured the ability of the radar receiver operator to make these distinction, and hence the name receiver operating characteristic. It comes from radar receiver operating radar receiver operator. Okay. We can also compute the area under this curve, right? So as I said, the more you go here, the area under this curve, which is denoted by this, right? Which is denoted by this, increases. This area increases as you move towards this direction, right? So you can also compute the area under the curve, right? The more the area, the better the classifier, right? It can be understood as the probability that the model ranks a random positive example more highly than a random negative example, right? The perfect AUC is one, which would be here. This would be the perfect classifier. the random AUC is 0.5, which would be the area under this random classifier curve. You can compute the area is half into base into height. Half base is 1, height is 1. So, and hence the random AUC is 0.5. The advantage of AUC is that it's scale invariant and classifier threshold invariant, right? Because you compute the AUC across all the thresholds. So consider the problem of classifying a mail as spam versus no spam, right? Assume that the emails are ranked by the classifier risk score, right? On the left is high scoring mails, which should be classified as a spam mail, and on the right are the low risk or low probability mails, which should be classified as no spam, right? And here is the ROC curve, which is again the plot of true positivity rate to false positivity rate, right? You plot the ROC curve as mentioned before by plotting the TPR and FPR at various threshold, right? Now, how do you select the best threshold, right? Or the best threshold below which you would mark as below which you'll mark as spam, and below which you'll mark as non-spam, and above which you mark as spam, right? So what you do is you look at this ROC curve. You typically look for the knee point, right? And that knee point is basically saying that, hey, at this knee point, your false positivity rate is low, but your true positivity rate is high, which implies you would mark the true spam as spam, and you'll mark the true non-spam as non-spam. There might be 10 to 15% for false flagging, which is okay for me, depending on my problem, right? So this is known as the operational point. It is the point at which the TPR minus FPR is maximum. Okay. Now, after talking about all these metrics, we'll talk about multi-class classification, right? Till now, we have only discussed binary classification. However, in the real world, the data is multi-class. So let's take an example of an image classification task. Let's say you have to classify this image to the model. Now, this image could be of a dog, it could be of a cat, it could be of a bus, car, human, traffic signal, and so on and so forth. There can be multiple categories. For ImageNet dataset, you have close to 1,000 categories, and for other, you have even 10,000 categories, right? So for such cases, we need to expand our capability of a binary classification to a multi-class setting, right? So there are two generally used scenarios for multi-class classification. Number one is one versus the rest, right? So in this case, let's consider this figure. There are three different samples of three different classes. One is of a triangle, one is of a square, one is of a cross, right? So what does your intuition say? You convert this into binary classification problem, three binary classification problem. The number one problem would be considering this as positive example, triangle as positive, and the remaining two as negative sample. You have one binary classification problem. You have another binary classification problem by considering these squares as positive and these as negative class, right? And you have a third binary classification problem by considering this as a positive class and these two as negative class, right? Then you train three different models, right? You'll get three different lines. If you get during test time, once you get a sample, you pass the sample through all the three model and select the model, select the class for which the value is most positive, right? So let's say a sample during test time comes here. You compute the prediction value for this model, it comes out to be negative. For this model, it comes out to be positive, and for this model, it comes out to be negative. And hence you'll say, hey, my new sample belongs to class number this, the square class, right? Similarly, or we can use a softmax based classifier, which is another way of converting, another way of multi-class classification, right? Now, recall that in your previous modules, you might have studied about logistic function that computes the value between 0 and 1, right? For example, a logistic regression output of 0.8 from an email classifier suggests that there is an 80% chance of that email to be spam and 20% chance that it is not a spam or a good mail, right? And the sum of the probabilities is 1, right? So in a multi-class softmax classifier, what you do is you for all the possible classes, let's say there are k classes, capital K classes. For each of the classes, you get a probability, and these probabilities sum to 1, right? And this probability for a given sample to be of the class K, small k, right? Let's say this is the image of a dog, and the probability that it belongs to a dog is given by e to the power wk xi, where xi are the features, wk is the weight vector associated with that class, and you normalize it across all the different classes, right? Let's take this example that let's pass this to a softmax classifier. The softmax classifier will give you probabilities that it belongs to dog with probability 0.8, muffin with 0.1, cat with 0.05, and bird with 0.05, right? So there's w k means you'll have a wk for w for dog, you'll have a w, different w for muffin, different w for cat, and different w for bird. Okay. Till now we have talked about classification metrics. Let's talk in brief about regression metrics as well. Consider n blue data points. These are your data points, right? Fx be the line that fits the data. It might so happen the best line may not pass through any data point. Now, consider this data point. The error is determined by yi minus f of xi. So this distance is the error, right? Using this error, you can compute root mean square error, which is the square of this error divided by the total number of samples across summed across all the samples, and you take a square root of it. Similarly, you can compute mean absolute percentage error, and you can also compute R square. R square is basically the coefficient of determination. It provides a measure of how well observed outcomes are replicated by the model, or more simply, it evaluates the scatter of the data around the fitted regression line, right? It is based on the proportion of total variation of outcomes, which is these error explained by the model, right? It's basically a statistical measure of how well the regression predicts the real data point, right? How well this line predicts these, right? So the formula is given by this. So y minus f of xi is basically the square of the error. Y minus y bar is the variance of the label data, how this data is varying across the mean of these labels. And R square is basically 1 minus residual sum of square and the variance of the label data. Okay. Now we'll move to some supplementary topics such as naive Bayes, k-nearest classifier, and so on and so forth. Okay. Now, the naive Bayes classifier is basically a classification technique which is based on Bayes theorem, right? And with the assumption that there is an independence among the feature. So if I talk in more simpler terms, a naive Bayes classifier assumes that the presence of a particular feature in a class is unrelated to presence of any other feature, right? So that means the features are independent given the class. Let's take an example. Let's consider a fruit, right? A fruit may, let's say the fruit is apple. Now that fruit will be considered as an apple if it is red, it is round, and it's about, let's say, 3 to 4 inches in diameter, right? Now, even though these features, without knowing that this is an apple, these features might be related, right? But if you know these features, if you know that it is an apple, right? So these features become independent of each other, right? So this is the naive assumption which you're making, right? In real world, these features may be related, but the assumption which you're making is given you know the class or the category of the data, these features would be independent of each other. So this is what it says. The class probability, the model computes the probability that this point xi has the class yi, which can be computed using the Bayes theorem as p of yi into p of xi given yi. P of yi you can compute from the data, and this p of xi given yi, now xi is an apple. An apple consists of, let's say, 3 features, right? As I said, red, round, and the diameter, right? So the Bayes theorem says that the features in xi are independent of each other given yi, and hence you can write it as the product of probabilities, right? So in naive Bayes classifier, there is no training as such, right? So there is a learning which simply involves computing the class conditional probabilities from the training data itself. You have to compute this value from the training data, right? Now the advantage is that the learning is straightforward. It's really fast during learning as well as prediction time, because there's no training involved, right? Just you need to compute these tables from the training data, right? So if you have 10 features and 2 classes, it would be a 10 cross 2 matrix. You need to just compute this 10 cross 2 matrix from the data itself. Now, as I said, there are cons to this as well, because it's naive. So the class conditional independence might not always hold. The smoothing might be required for sparse features, right? Now let's move to k-nearest neighbor classifier, right? The k-nearest neighbor assume that similar thing exists in close proximity with each other, right? So let's take this example. There are 2 classes. The samples of class 1 are close to each other, and sample of class 2 are close to each other, but the samples of which are not, which are of different classes are far apart. So this and these are far apart, whereas this and this are close. Okay, so how do you compute when a new point comes, right? Let's say this cross is the new point during test time. What you do is you look in some local neighborhood of that point. Let's say you find that in this local neighborhood, there are 6 or 7 points, and all the labels of those 6 and 7 points are blue, and hence this new point would be labeled as blue, right? It can also be used for regression. So instead of classifying this point, you compute the average of this point, and this would be the regression value for this new point. The nearest neighbor may be calculated using KD tree and probability semantic hashing. Okay. Now there is an effect of the neighborhood size, right? This neighborhood size can be this big, it can be this big, it can be this big, right? And hence uh, the boundary or the separating boundary which you get from the k-nearest classifier varies, right? If the k is very small, you get jagged boundaries, very jagged boundaries. You can see pockets and all. So it is a nonlinear classifier, but if the k is very small, the boundaries you get is very jagged. However, if you take a huge neighborhood, so you sort of average out the variations, right? And hence you get a smoother boundary between the two classes. Okay. However, k-nearest neighbor suffers from the phenomenon known as curse of dimensionality. Now, um, what it says is, as we move to higher and higher dimension, the data fills less and less space of that dimension, right? And hence, in order to maintain an accurate representation of that problem, you need more and more samples. So the number of samples have to grow exponentially. So this is the curse of dimensionality, right? So let's take this example, right? Um, so if you're able to see the screen properly, let's say you sample 10 to 15 points or 20 points uniformly in the range 0 to 20 in one dimension, right? And consider these 5 regions of length uh, uh, 5, these 4 regions of length 5 each, right? So to have these 20 samples, you just need 4 regions. You have 4 regions, right? Uh, but if you move to 2D and you randomly sample from 20, uniformly randomly sample from 20 cross 20 grid, and let's say 15 to 20 samples, you see there are 16 regions, right? And a majority of the regions are empty, right? Similarly, if you go to 3 dimension, you'll have 64 regions, right, for 20 samples. So a majority of those 64 blocks would be empty, right? This is what this right figure is trying to say, that as you go to higher and higher dimension, the number of samples in each of those cubic region, right, which is in this example 5 cross 5 cross 5 for 3 dimension decreases, right? Okay. There is another problem associated with curse of dimensionality, right? Let's consider a fixed number of random points are generated from a uniform distribution in D dimension, where D can be 1, 2, 4, and up to 128, right? What we do is we compute the pairwise distances across all these random points. Let's say we have k random points, you compute k square distances. and then you normalize them by the maximum distance. What do you do here is then you plot, right, the frequency of the distances, right? Since the distances are normalized, so the value will lie between 0 and 1. And on the x-axis, you compute the frequency of those distances, right? What's the number of samples which go in the range between 0 to 2? It's close to 1, so on and so forth. So most of the there are multiple samples in the range 0 to 2, 0.2 to 4, and 0.8 to 1. Now, but as the number of dimension increases, right, we see that the spread decreases, right, as the number of dimension increases, right, which implies that more and more samples have similar distances, have same distances, right? Let's say here in 128 dimension, this is peaked at 0.6. So what you can conclude is more and more samples have a distance of 0.6. Any pair you choose, and that pair would have a distance of 0.6. Now, as explained before, k nearest neighbor works on the distances, right, on the neighborhood. Now, if all the distances are approximately equal to 0.6, right, k nearest neighbor would fail, right, and hence it is good to work in for k nearest neighbor to work in low dimension spaces. We can also talk about support vector machine kind of classifier, right? So let's take an example, right? So this is the samples of positive class. This is the sample of negative class, right? You have 3 different options to choose, right? This is the red line, green line, and blue line. What do you think is the best line, right? The blue line is a decent classifier because it separates the two. The green line is also a decent classifier because because it separates the two. However, if you consider this gray test point, right, the blue line will make a wrong decision, right? But just on visual inspection, you'll see that this belongs to the positive class, right? So the green one actually classifies them the best. Right? Now, the interesting feature which I've not mentioned is the gray dotted line, right? These lines represent no man's land in which no observation should fall, right? So this each strip of these gray line can be viewed as a margin of error, right? Because no sample should fall here. Now, these two margins are computed as the parallel lines that maximizes the distance between the samples of the two class. So this is the distance between the samples of two class, and these lines are plotted such that the distance between the samples of two classes is maximized, right? These line passes through some of the samples of class 1 and some of the samples of class 2, and these samples through which the line passes are known as support vector, right? So now you have an answer to the question why green line is better, because the margin or the separation between the two classes is maximum for the green line, right? The core idea of the SVM is to maximize the margin under the constraint that the classifier does not make any mistake, right? Okay. So the SVM solved the following optimization problem when the data is linearly separable, right? You would want that all the samples of class 1 are on the right hand side of the this margin. All the samples of class -1 are on the left hand side of this this gray line, right? Which is equivalent to saying y w transpose xi plus b is greater than 1, and the margin is denoted by 1 by norm of w square. So what you would want is to maximize the margin, right? To maximize this inverse function is equivalent to minimizing the opposite of this, which is minimizing half norm w square under the constraint that the samples of class 1 should be above this, the samples of class -1 should be below this, right? And hence you get w transpose xi plus b equal to 0 once you solve this problem as the model, SVM model. However, there are cases when the data set is not linearly separable. In such cases, to obtain a linear classifier, barring few errors, you use a slack variable. Let's take this example, right? So these 2 points make the data set not linearly separable. However, you can make them linearly separable by pushing these here and pushing these here. And this is what slack variable does. It pushes these points out of this margin area, right? And hence you get an optimization problem of this sort. Not going into detail here. There is another case, right? Till now, we have only talked about linear classifier, right? Even after adding slack variables, you'll still get a linear classifier, but there are cases when this might not hold. And in fact, in most of the cases, this does not hold, right? Consider this case, right? You have two concentric circle, one here of class one here of class -1. There is no line you can make which would separate the two. However, you can do something um, clever, right? You can transform this data into polar coordinate, right, by x square plus y square. In this polar coordinate, this data set is separable, as you can see here. And then you can draw a line, right? You can use an SVM in this space, right? And if you turn it back to the original space, this line correspond to this circle, right? So this is known as transformation using a function or a kernel, right? You transform xi into some z of xi, this z space in which the data set is linearly separable, and you perform an SVM. Typically, SVMs are solved in dual form of the optimization. What I showed you initially was the primal. You can convert into a dual format. The advantage of the dual format is it allows for creating a non-linear mapping Z without explicitly computing this Z, right? You can, because in this dual form, you have the dot product of this mapping, and this dot product can be some function which you choose, right, based on some properties of the function, right? This can be a radial basis functions shown here. It can be a polynomial function. It can be a tangent kernel, right? So this is an example. Consider this 2 moons data set, right? This is not a linearly separable data set, as you can see. If you use nearest neighbor with some neighborhood value of k, you would get this kind of a classifier, and you get close to 97% accuracy. If you choose a linear SVM, you only get 88% accuracy. However, if you choose a RBF SVM, that means you're using this function, right? That means you're mapping it to some higher dimension using this function. You get this kind of classifier and you get 97% accuracy. Okay. Lastly, we'll talk about model selection. Till now, we have only discussed evaluation metrics and some classifiers. Now, right? For a given problem, you typically have to train several models and then select the best model. Now, for each model, you also have several knobs to tune, right? Now, we'll now talk about how to select these best model type out of all the models which you have trained for a problem across various settings of these knobs, right? And this is known as model selection. Now, typically, you for a given problem, you train several different models and select. You want to select based on some metric, right? And here we provide a paradigm for proper model selection, right? Uh, Typically, you get your data is shown here, all the data. What generally people do is you train on this data only and test on this data. This is incorrect. Ideally, what you should do is you should keep a part of training data separate, call it as training data, keep the part of all data separate from the training data and call it test data, right? And then you should train here and then test your model here. Typically, different classifier, as I said, have different hyperparameter or knobs you can tune, right? Let's say for linear model, you have regularization coefficient. For SVM, you have C, gamma, and other coefficient. For random forest, you have number of trees, depth, leaf size, and so on and so forth, right? So let's say we have decided on a metric, right? That metric is accuracy, right? And then what you want to do is select the best possible value of the knob or the hyperparameter for that decision tree, for which you get the optimal performance on the test set. So what do you do is you consider the train and test set of the data. You consider, let's say you have, for example, you consider only the depth of the tree, right? You build a decision tree with the maximum depth, compute the train and test accuracy, then you choose this depth 1, depth 2, depth 3, depth 4, so on and so forth. You compute the train and test accuracy, right? So you'll get a plot something like this, right? For a single test train partition, right? For one depth, the accuracy is 0.6. For 4 depth, it's 0.9, and so on and so forth, right? And after this, the accuracy does not change much. So ideally, you would select this model as your best model because train and test curve follow the same similar curves, and the best accuracy on the test you get here at 4. However, when evaluating the hyperparameter, there's still a risk of overfitting on the test set, right? Because the parameters you have tubed are on the test set only, right? Now, this way, the knowledge about the test set can leak into the model, right? And model might not perform well on new unseen data apart from the test set. So you have taken one test set, perform everything there, right? You selected the best parameter. However, when you go to the real world real life data, the model would fail because it has only it has been tweaked the best for the test set only, right? To solve this problem, so what we do is we create yet another partition of the training data known as validation set, right? Initially, you had all the data, you perform 2 partition, now you perform 3 partition, right? Yellow, green, and blue. Okay. Now, a test set is still held out for the final evaluation, right? The issue with this kind of approach is, since you are dividing into 3 parts, the number of training samples would reduce drastically, right? And hence, when you perform the hyperparameter tuning on this validation data and perform on test data, the performance might not be as good, right? So what you do in this case is you do a k-fold cross validation. What you do is you take this training data, divide into, let's say, 5 segments. You can divide into more or less depending on the problem statement. Typically, people divide it into 5 segments. You consider one of the fold as the validation fold and the remaining as training fold, right? You combine these 4, train on this, tune the hyperparameter on this. In the next step, you train on 1, 3, 4, 5, validate on 2, and so on and so forth. And then you take the average out of these, right? And based on this average value, select the best hyperparameter. And then finally, once you are happy with the hyperparameter setting, you take that hyperparameter setting, train the model on this data for that given hyperparameter setting, and test on this data. Okay. Now, there are multiple ways to do hyperparameter tuning. One is grid search, one is random search, right? Grid search, you take all the parameters, keep them in nested for loop, and then perform k-fold cross validation on each, determine the average error, and then select the best parameter based on the average error. There is also another type of parameter search which is known as random search, right? You fix a number of iteration, you select these hyperparameter, each of the hyperparameter randomly from a certain range. You perform a k-fold cross validation and determine the average. In this case, there is no guarantee that you would find the best parameter because you're not going through all the parameter. You're only going through some number of iterations. However, this is typically faster and you can do a parallel search here. Lastly, I'd like to leave you with some of the modeling tips for training and testing of the model, right? Typically, as we see in machine learning and with the emerging deep learning technologies, more training examples, the better, right? Because the larger training set leads to better generalization on unseen examples. The more feature is typically better, right? Typically people invest time in feature engineering to construct the optimal set of feature for a given signal. As I said, people typically make mistake by evaluating the performance on the same data as which was used for training, which is wrong, right? And then you should perform k-fold cross validation if your model permits that. You should pay attention to training data quality. This is the most important part here. Typically, you would find data from which are open source from universities and all. They are typically of good quality. However, if you get data from non-open source, or you get data which is coming from transaction data and all, the data might not be very good, right? So you need to remove outliers, you need to remove target leakers, you need to remove garbage data and so on and so forth. So that is the most important. If your data quality is bad, the model trained would be bad, right? So this is the most important thing to take into account. And as I said, one metric might not be always appropriate. It depends on the business objective. You need to retrain the model periodically because there might be data drift, because let's say people would buy different kind of clothes in summer versus winter, right? So a model which is trained for summer clothes won't work for the winter clothes. You need to retrain it depending on the time of the year, right? And we should also ensure the training data distribution is in sync with the test data distribution. If the distribution of the two are different, the model will obviously fail, right? So these are some of the modeling tips I'd like to leave you with. And that's it from my side. And I'll leave it open for the questions.